welcome to Chapter 10. The title of this chapter is called Space, the Final Frontier. If you know anything about Star Trek, that is like one of the opening lines in the old show. You know, and I am Captain Kirk, so I had to make that joke. This chapter is not about outer space, believe it or not, even though the picture on page 415 and 414 has a picture of a galaxy. The chapter really is just introducing three-dimensional geometry. So remember we had to talk about plane geometry and then we talked about area. Well, we're going to talk about space and 3D geometry before we talk about volume. So this is a very important chapter. Our first section, 10.1, is perspective in space, and we're going to be drawing some 3D figures. Okay, so a drawing that captures real-life appearance is a perspective drawing. There's two main components of perspective drawings. One is the vanishing point and the other is the horizon. So we're going to talk about those definitions here. The horizon is at the eye level of the observer, where the vanishing point is where the parallel lines look like they're meeting. Okay, they still are parallel, but on a perspective drawing, they don't look like it. They look like they touch at a vanishing point. So there's a type of drawing that doesn't have a vanishing point, and then there's a 1 point, 2 point, and 3 point vanishing points, and we're going to look at all of those. So here is a 1 point perspective where we have one vanishing point on the horizon, and if you look, there are still three sets of parallel lines. The first set is going along where they would vanish on the vanishing point. These are the ones that are kind of tough to draw. And then we still have this set and this set of parallel lines. Now this is a rectangular prism, or you might think of it as a box. So if I'm looking at it from this perspective, I don't see the other sides. There's actually 1, 2, 3, 4 sides I don't see. I only see the top and the front. I don't see the sides or the back or the bottom. And then I have a 2-point perspective where I can see three sides of the box, okay, and I don't see three sides of the box. The other thing that's important with the 2-point perspective is once I have two sets of parallel lines going to two different points, I can draw the horizon now because I have 2 points and all I need is 2 points to draw a straight line. My other set of parallel lines are right here. And last, we have a 3-point perspective. These are the most difficult concepts to grasp when you have a 3-point perspective. But they're also, 3 points are the most realistic on they look the most like a photograph. But if you see here, there are 3 sets of parallel lines. I can still only see 3 sides, but I'm kind of above, my point of view and my horizon is above the object. So this would be very realistic looking, say if this was a building and I was on a balcony looking down at the building, this would be most realistic is a 3-point perspective. So notice 2 points go to the horizon and one has a different vanishing point below. Now there's also pictures we can draw that have no vanishing points. See, if I have 3 sets of parallel lines and all 3 sets are still parallel, this is where the horizon is actually equal or even with the figure itself, and it's called an isometric. We only have one theorem to go over, and it's theorem 10.1. If the endpoints of a segment are equidistant from 2 other points, then every point between the endpoints is also equidistant from the other points. So as usual, we need to look at a picture because this is a lot of words to decode here. this is the picture that we're going to work with. It's basically saying that if I have 2 points, P and Q, that they are equidistant from A and equidistant from B. If that's true, then they are also equidistant from any other point that I would put on the segment AB. Okay, so let's go ahead and break this down as the proof. So a given would be that I have a segment. I have segment AB, and then I have 2 points that are also given. And now those are the distance from P to A is equal as the distance from A to Q. And also P to B is equal to B to Q. Okay, those are all given things. And now I can also say that those are congruent, because remember, that's the definition of congruency, definition of congruent segments. And same with these segments. Those are now congruent by definition of congruent segments. And then I know AB is congruent to itself by reflexive property. So if you look here, I now have 2 congruent triangles by side, side, side. So that means all of their angles are also congruent. That brings me to the next step, that these 2 angles are congruent by definition of congruent triangles. And now I need to have that extra point. This point is actually given. It's the way it's worded in the proof on page 418 is that X is between A and B, because it says any point on that segment is going to be equidistant to those points P and Q. Alright, so now I know that AX is congruent to itself by reflexive property. And now if you look carefully, I now have 2 sets of congruent triangles again by side, angle, side. So those 2 triangles that I've highlighted there are congruent to each other. And if that's true, then that means all of their parts are congruent. So that now I have proven that XP is congruent to XQ, which if it's equidistance means that XP is equal to XQ in its measure. And then I'm done. The end. The last thing I want to touch on is intersections of planes through figures, because this is also a little bit difficult to draw. So if I'm getting better at drawing a 3D figure, this is a triangular prism, and I'm going to put a plane through the figure. Now, if you look at the cut lines here, those little purple dashed lines, it's not at a right angle. It's not going straight up and down to the bases. It's going at an angle. So if it looks like this. Okay, so you have to imagine that's a giant wedge of cheese, and the plane is the knife that's going to cut the cheese. Okay, and the little blue dash lines, that's the shape that would be if I could open up the wedge. Okay, which would be a trapezoid. Hopefully you can kind of see that. It's, like I said, it's hard to draw 3D figures on a 2D surface and really get an idea of what I'm talking about here. Okay, if I haven't said enough times, don't worry if this is hard for you, okay, to draw these figures. You will get better as you practice, but you have to practice. So now we're at our WSQ summary, and I would like you to do this on graph paper if you have it. It will just help because you'll have a horizon that you can go to, and you'll make nicer pictures if you use a straight edge and graph paper. So I want you to try to do these 5 figures. I do want you to email it to me. Now the thing that's not going to happen is I'm not emailing you back the answers. You'll just get a reply that I received it, but I'm not going to give you the answers. I want to go ahead and review all of your answers, and then in class we will go over this. So I will see you in class.